All right, welcome back to Calculus 3, everyone. So in this video, we are going to begin the new chapter 5, especially focusing on 5.1, double integrals over rectangular region. So it sounds like, very comfortable because we know how to take the integral, correct? So Calculus 2 was all about taking integral, and there are different techniques. So we know how to take the integral. Although there is a word double, it sounds like we are taking twice, right? But why? Because in this topic, you are going to find out the region. So if you remember, just a little bit of background of using integral in many different fields. So integral is like this symbol, right? We talked about it a lot in Calculus 2. So integral, you have a different function. So depending on the function, it could be linear, quadratic, polynomial, rational, whatever trigonometric function. Depending on the function, the integral technique is different, right? So that's why you have an integral table. If you have exponential function, this is the outcome. If you have a trigonometric function, we have a different techniques. So what we are going to do in the chapter 5, as you know, we are not talking about one variable because this is a Calculus 3. You have to deal with a multiple or more than two different variables because your variables coming from different XYZ axes. So we've been expanding our knowledge from 1 to 2 variables to take the integral or to take the differentiation, correct? So let me go back to Calculus 2 because the integral, it's really, really, really funky. And it's very unique because it helps us, if you remember, it helps us to find out the area, right? So if you have a function in Calculus 2 with the one variable, it helps us to find out the area from A to B, correct? And also, if you have the three-dimensional image, it also helps us to find out the volume because you can rotate it, this function, either x-axis or y-axis. You could find out the, that type of shape, and you can find out the volume. So we talk about shell method, cylinder method, things like that. So the purpose of using integral, not only just find out the area, but also you can find out the volume, correct? What else? What else we can do? We can also find out the arc length, if you remember. Although this is not linear, but by using the integral technique, you can find out the length of the arc, right? Because you can find out many, in the line, you have a many infinite number of the points. So you can find out the linear, small linear. If you keep adding them, it's going to be create the arc lengths. And also you can find out the surface area. Also, it helps us to find out the force, things like that. So there are many ways you can see, using integral. And then, these are the example: finding area, volume, arc length, surface area, force, or in many physical application, you've been observing, how the integral help us to, give you that answer. So what we are going to do, very similar one in Calculus 3. So as I mentioned, Calculus 3, it's like accumulated concept from Calculus 1 and 2, just we are dealing with a couple different variable. Now, do you see that region? Okay, so by taking double integral, we might be able to, so in the three-dimensional space, so let's say you have x, y, and let's say you have like whatever this, I'm just trying to draw. Let's say we have this image, okay, in the three-dimensional space, okay? I'm trying to draw. So this is a three-dimensional image with that function. Let's assume this is what it is. And then by taking the integral, we know that it helps us to find out the area or region volume. So here we are dealing with the two variable. So you can think about it. Oh, we have to take the integral for x variable and y variable because we are dealing with two variables. So very similar what we did in calculus 2. We've been using only one variable, but we know that the purpose of using integral to help us to find out so many things. So that's why we are taking double integral to find out the rectangular's region, rectangular's volume, or many in application, physical application. Does it make sense? So let me show you. So this is like a more extended knowledge from calculus 2 to 3. I'm gonna show you the image, what I'm drawing here. So here's the image, okay? So we have a function. We don't know what that is, but anyway, there's a function that show you this image. So it is a three-dimensional image because that function has a two different variable in three-dimensional space. So what happened is the goal is, I want to find out the region of this rectangular shape. Okay. Later, we're going to find out the volume of entire this shape, but let's think about step by step. We are going to be given the function, and then the question is, are we able to find out this region in this three-dimensional space? And then this region is corresponding to this function. Okay, so this is like just one image of the kind of like cross-sectional image of this shape, so that you can think about there are many accumulated cross-sectional image inside of this shape. But as long as you know this region, then later you're going to find out the height. Maybe you're able to find out the volume as well. So the idea is here. I want to consider the following space. This is the space here. And then, this space exists above the rectangular region R. Okay. We assume that there is a continuous function, which means there's no hole, there's no break. Whatever this function is continuous, and then is given positive with two variable. Okay. And then they actually gave you specific range for x-axis and y-axis. Okay. So in this image, I'm not really, take a look at the z-axis. I'm not really care about the z. We are just care about the x and y variable here, two variable. Because if I consider z, it's going to be more complicated. We just think about two variable first. So here is a given. If you have the specific range for this R, which means, I'm going to change the color. In the x-axis, your region is going to be between A and B. Does it make sense? So there is a specific range for the x-axis. So that's what I consider, or you can write down either way. X is between A and B, or A, B included. It's a closed interval, correct? Same thing when I look at the y-axis, because y variable from the y-axis, so it's going to be between C and D. Again, y is between C and D. You can write down either way. So this is a given. If you have this situation, am I able to find out the region? In other words, am I able to find out the volume of this shape? Yes, because we're going to use integral, in this time, double integral, because you have to take the integral with respect to x and y separately. Okay, so if you remember, so I'm going to just keep using the calculus 2 concept because it's very understandable calculus. Everybody loves calculus 2. I hope so. So what was the way to find out the area? So if you remember, A to B, we create many equal size, equal length of the rectangular. Do you remember that? So here, you're going to find out equal lengths of the rectangular. So if your summation, if you're adding all the equal size of the rectangular, we might be able to estimate the area under the curve. We call that was Riemann sum, right? So the Riemann sum help us, by taking the integral, by taking all the summation of the, so this is the function, and then this is the height, each rectangular's height times equal length, that's a partition. And if you're adding this, if you're multiplying those two, that's the one area of the rectangular. you are adding everything from 1 to n, right? So n equal to 1, infinity. So that's the Riemann sum. Later, this information change it to the integral, just simply like that. So we can apply this concept into here. So again, you're gonna have many, many, many equal size of the partition. So what I'm saying is, in here, so if you look at this x-axis, I just converted this image. So this is the x-axis. You see that? This is the corresponding to the x-axis parallel line. So I have all, so this is from A to B. Am I correct? I'm gonna have equal length of the partition. So you're gonna have a many, 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 many equal length. So that means triangle X, which means, you know, whatever the B minus A divided by N, you can find out the equal length. So you have an equal length of the rectangular. Does it make sense? So you're gonna find out the partition on the x-axis. You're gonna do the same thing on the y-axis because that's gonna be your equal lengths before you're gonna multiply with the height. So same thing here, this is y-axis. We have a from C to D, am I correct? You don't need to memorize, just try to understand. Because to find out the Riemann sum, you need a partition, the equal length. This is the equal length on the x-axis because we have only one variable, but now you have a x and y two variable, you have to find out two, right? The two equal lengths. So this is gonna be D minus C divided by N because we don't know how many number of the rectangular. So that's it, that is gonna be the equal lengths of the y. So you have many, many equal lengths. Right? So we good. So far, so good. Then what? We're gonna take a look at the Riemann sum because by keep adding. So this is the function. Is a given. X, Y is a given. But your height is going to be changing depending on the X, depending on the Y. What I'm saying is if you have here, so you have this volume, you have this volume, you have many, many rectangulars of volume. You see that? It's hard to draw, but you have many. You have many inside here. Many, many, many rectangular. So that's, everything has a different height. This one might be longer than this one. This one might be shorter than this one. So that this is the height times the area, right? So what happened is, this radical x times the radical y, so radical, the equal lengths on the x-axis times equal length of the y, we call that is A. So if you do multiply the region times the height, and then you are adding all the summation of the infinite number of the rectangular here, and then take the limit, ooh, we can find out the volume. So that's how this formula came from. Nothing is special. We're literally using from the calculus 2 concept, okay? So that's why we are taking double integral later, this formula, changing to the limit and the summation. We know that that's converted to the integral. So we have a double integral, whatever the given function times equal lengths. That's how you're taking the integral. That's from this Riemann sum. So we're gonna take the double integral of the function 2 with the 2 variable over the rectangular region to find out the volume of that shape. Does it make sense? So I think this is the easiest way that I can convince you how to find out the volume of the 2 variable of the function, because it is the same thing from the Riemann sum with the 1 variable. Okay, so there gotta be a reason, right? Why we are taking the double integral, because in this variable, you are dealing with 2. So you have to find out double integral, you know, one is for the X variable, one is from the Y, for the Y variable. So that's why same Riemann sum gonna be applied into this 3-dimensional space to find out the region with the 2 variable of the function. Okay, so you can modify a little bit. So M and N, it's the same from, one is from the x-axis, y is from the n is from the y-axis. We are trying to reduce the gap smaller, and then this is the same height times the the region of the rectangular. So you're going to adding all the summation of the, volume so that you can find out the total volume under that, function. Okay, so that's how we're going to use, that's why we're going to use this formula. Okay, so now I'm going to show you the example how to apply this, the formula that we just discovered into the following question. So I'm going to go to the following question. Are you guys okay with that? If you got that one, I love to see your thumbs up. Okay, so nothing is special. We got this concept. So now I'm going to move down the following question. So you can take a look at it, what's happening. So this is the example that I want to show you. So here we go. As you see that in this function, we have a two variable, X and Y. And then this is the image. Okay. And then they are going to have the region from 0 to 2. So this is the x-axis, interval. And then this is the y variables interval, of this region. So they want you to actually at the end find out the volume of that shape. So we're gonna step by step. So there's sub 3 question. So let me read the A. Set up a double integral. Yes, we're gonna take the double integral because we are taking two variable. For finding the value of the signed volume. So we're going to find out the volume of that solid shape that lies above the R. So we know something going on. So you have a infinite number of the rectangular volume, in three-dimensional space. So you have a many, rectangular. One is a higher, one is a shorter. So that's something going on. I want to find out the volume, isn't it? So the double integral, we just talked about it. It helped us. So to find the volume, the letter A, volume equal to, what we're gonna do? We're gonna take the double integral, and then the function is a given. So let me just write down first the A. So the double integral, we are looking at the region, and then the function is what? 3x second minus y. And then as you know, dA is the multiplication between the equal length of the x times equal length of the y. So anyway, that's a dA, that's okay. This is the area that's represent the region R in many, rectangulars in this shape. So anyway, that's your double integral. And then I can rewrite it in terms of the Riemann sum, okay? So what happened if you go up, this is the Riemann sum version. This is the integral version. They're same, corresponding to each other. Riemann sum, integral came from the Riemann sum idea, so we can rewrite it. So now I'm going to change to limit, and then according to the formula, mn approach to the infinity, because your rectangular, we don't know how many, it's keep going larger and larger and larger. And then n1 is the summation from 1, another one is a j, and you have 3x, because in this time ij, because if you choose a one, small rectangular, one side is with respect to the x variable, another side is with respect to the y variable. So that's why fxy, and then in this time it's a second power. I'm going to do the second power minus the same thing yij. This is a keep changing depending on your I and j. If you want to choose this one, it might be, x, 1.3, and, y is like a 2.0. So there are many variation for I and j, because we have like infinite number of that. So that's going to be, at the end, we're going to have, oops, sorry. We're going to have triangle A. So that means, partition X times partition Y. So that's, you can set it up. That's letter A solution. We just set it up. Nothing is special. I'm not calculating yet, but you can think about it, how to set up this double integral and how to set up the the Riemann sum. So I'm going to hold up here. I'm going to move on to the letter B. Okay, so now we are going to take a look at the following question, B. divide r into 4 squared. So what happened is, if you can imagine, so there gotta be a reason here. There is a region under this function, okay? It's hard to imagine, but there's a region, you know, below this function, right? Because that times height gonna be the volume, correct? But they said divide this r into 4 squares. So I'm gonna just bring this one. So this is the r in the bottom, and I'm gonna rotate it because I wanna just make it simple. So one side is corresponding to x axis, another side is corresponding to y. So this is x, this is y. I just rotated it a little bit. So we have a region, something like here. They say divided by this r into 4 squares. So I'm gonna just follow what they're asking you to do. So here, I'm gonna divide it by 4 different square, right? So square means all 4 sides are equal. Am I correct? So each side, everything is gonna be equal. Okay, I got it. And they say m equal to n equal to 2. So what does it mean? So the m is gonna be, ending number is 2. That's what they're saying, because the ending number is 2. So the x, we stop here at 2, 2,0. Here, and on the y-axis, we also stop 0,2. Does it make sense? I'm not creating the story. I'm literally following what they're asking you to do. So that's what we got. So divide r into 4 square, and the ending number of each m and n is 2. So we know where they're actually stopped, 2,0 on the x-axis, 0,2 on the y-axis, and choose the sample point as the upper right corner on corner point of each square. So actually, they give you more specific point, the corner point. So these are corner point. So since this is equal side, automatically you can fill it. This is gonna be 1,0 because everything is gonna be equal side, which is 1. Am I correct? So here, what we can do, the partition of x is also 1. Partition y is also 1. Does it make sense? Because they must be equal length. That's the square. And then we know the ending point is 2. So the each length of the square should be 1. That's the option. That's a length. So this is going to be 1,0. And this is going to be what? 2,1. This is going to be 2,2. This is going to be 1,2. And then this is going to be 1,1. Right? So anyway, that's what they gave us also. 1,1 there, 2,1 there, which is, actually 2,1 is right there, and 1,2 there, and 2,2 there. So we have all the information. Now, by looking at this region, this is still region, right? By looking at this region, find the volume under the function we give 3x second minus 1. So we got it. We got it. So I got that what they're actually asking you to do. So we have 4 different squares. That's going to be your region. And then we have a specific point. So anyway, let's find out the volume. Okay. So the volume will be what? According to the Riemann sum, I'm going to use the Riemann sum. So we have the limit. So I'm going to skip the limit for a second because it's not going to be infinity. We actually stop at 2. So we don't need to write limit because we know the ending point. So let me write it first. And then this is going to be the ij, comma, yij. This is the Riemann sum without limit because we know it does not go infinity. It does not go to infinity. We know each ending point is a given. One is a 0,2, another one is a 2,0. So therefore, I can rewrite it. M is a 2. N is a 2. This is a J. And then we do have F, right? We have to write it again. So here, Xij, comma, Yij, A. Are you okay? So let me just minimize it because I need more and more space. So let's continue. What does it mean here? So we do have, right now we can calculate it, everything. So we can rewrite here. So this is the 4 combination. We have a 4 combination here, 1, 2, 3, 4. So the first one, you can start this one. So this means you have 4 different regions inside of the entire region. So one is going to be F. What do you guys think? X11, because we have only one option. I go to 1 and stop 2. J go to 1 and stop 2. So I X11, comma, Y11 times A. That's the region, the multiplication, this 2, plus the next one. What other combination? 1, 2, Y, 1, 2, sorry, 1, 2. 1, 2, and A. And then what is the next one? X to 1, comma, Y to 1. And then last one is a 2, 2. We have only those 4 options because N, M, they're stopping at 2. So the last one, X to 2, Y to 2 times A. So I'm not doing anything special. So this meaning you have to adding 4 different combination. Okay. So in other words, X11, right? What does it mean X11? So you have X1, Y1. So they're actually stopping here. So this means F1, 1. And then this one, what is that? If you multiply A, it's going to be 1 because A, it means X partition X times partition Y. So every triangle A is going to be 1. Second one, 1, 2. So I have 1 up to, right? So that is going to be 1, 2. So F 1, 2 times 1. The third one, I have a 2, 1. So it's going to be 2, 1 and times 1. Last one, we have a 2 and 2, which is F2, 2. So exactly these numbers are given. And you can actually find out from our corresponding position. But this is actually given here too. So anyway, just time to calculate it. So we have a given function. So I'm going to minimize a little bit. Sorry, guys. So we have a given function right there. F x comma y is a 3x second minus y. So you're going to plugging in 1, 1. And what is it? It is going to be 3 minus 1 is a 2. 2 times 1. And then if you plug in 1 and 2, 1 go to x, 2 go to y. So 3 minus 2, that is going to be actually 3 times, 1. So we're going to get 1 times 1. And if you plug in 2, 1, 2 times 2 is a 4, 3, 12 minus 1, 11 times 1. The last one, you're going to plug in 2, 2. I have 12 minus 2, so 10 times 1. So if you're adding 2 plus 1 plus 11 plus 10, at the end, you have 24. That's the volume with the specific, length, equal length of 1. And then when you have a 4 specific, triangles. So that's how you find out the volume, by taking the limit sum. Later, I will show you how to take the integral, but this is the traditional way you're literally using the limit sum. So, this is very good question. I think this is a good question to understand how this concept can be related to finding the volume, okay? So take a look at it. You can change whatever the the region, you can have 8 squares, whatever, but this is the beginning step. So think about it. So we're good to go. So that's how you find out the volume in this context. Okay. Okay. So I'm going to just hold up here. I'm not going to rush. Chapter 5, it's actually not really difficult. Just the idea, it's accumulated. So think about it. If you got that one, I'd love to see your thumbs up. How you feel? Does it make sense to you? I think a couple people good to go. So definitely you can understand that, right? This is not something crazy question yet. So you got that. So let me take a look at the C. Ooh, here we go. One more example. Oh, I think I need a space. So here, let me read it. So it's the same thing like what we did in letter B. So we're gonna divide R into 4 squares. So that's the same context. You have a region, and I'm gonna have 4 different squares with the equal size. So square means every side of the square is equal. So they say ending number is 2. So it's the same shape. So literally, I'm gonna copy this. So copy, and then here's C. Let me change the color. So the C here, and then it's the same thing so far. Nothing is special. So the ending number mn and 2, so we know the exact point. Okay. So we have xy should be 1. The equal length should be 1 because ending number is 2. So the partition of the triangle A is going to be 1 as well. Okay, so that's good. So let me keep reading. But in this time, they choose the middle point. So what is the difference between B and C? They used to choose the corner points to find out the volume, right? So that you find out this one times, height, this one, this is a height times the, region area, we keep adding. But the difference is B, we focusing on the upper corner, which is a corner point. So the B, we focus on the corner point to achieve the same goal. C, we are using the midpoint. Okay. So the midpoint is going to be here. We have a 1,1, but instead of choosing this one, you're going to choose a midpoint, which is here. So here, the middle is here. 0 and 1, the middle is 1/2. 0,1, the middle point is here. So they're choosing the middle point in each square instead of using the corner, because it doesn't matter. You have so many, points in this region. They are trying to change their perspective to find out the, the volume. Let's, use the midpoint. What we're gonna get. So let's try. We're gonna try to use this one, middle point. So it's already given. We don't need to evaluate it. Everything is given. So simply, you're gonna plugging in. We already know. I'm gonna just literally copy this one. Copy, and I'm gonna paste it here. So the step 1 is we're gonna use volume equal the ending number. Actually, you know what? I'm gonna just copy this too. Copy, because it's the same. Letter A and B are same, isn't it? So let me just copy those two and paste. And then now this one, they're using the 4 point. So the 4 point is given, the 4 middle point. So let me use that. So if you now the 4 different combination. So one is 1/2, 1/2 times triangle A plus, what was the last, another one? You have a 3/2, 1/. This is another middle point here, right? So that's what we are doing. And then the another point was 1/2, 3/2 A plus the last one, 3/2, 3/2. I need a little bit space. So that this one. So now same thing. you're gonna calculate it, plugging in the given, your function, fxy equal to 3x second minus y. So you're gonna plugging in 1/2, 1/2. Actually, I already calculate that for you. And we already know triangle A is 1. So that is going to be 2/4, right? 1, please read, you can calculate it. And then if you're plugging in 3/2 and 1,2 into here, you should get 26/4. Okay. And then if you're plugging in 1/2 and 3/2 into that, you're actually going to get the negative number and times 1. Oh, I forgot 1. Plus last one, plugging in, you should get 21/4. Okay. Okay, so if you now finalize all the summation, I got 45/4. So if you change it to decimal, let's check. What are you going to get? 45 divided by 4. 11.25. Okay. So now you might be questioning, Professor Ben, why we have a different answer? So we are approximating the answer. We are not 100% sure. If it's really difficult to find out the volume, one method, if you're focusing on the corner, we got 24. If you're focusing on the middle point, you got 11.24. Again, many statisticians and mathematicians, they are going to calculate based on other points. It could be like close to the left corner, or you could choose a close to the left corner, whatever. There are so many infinite ways you can find out the volume. So at the end, the true volume, the actual volume, is going to be between some number and some number. These are possibility. We don't know this is 100% sure, but just, you know, the approximate answer can be different because of the choice of the sample points. Okay, so that you have to test multiple times, and actually you are going to find out the range to find out the actual volume. Okay, we need to investigate more, but the idea is later you're gonna choose, you're gonna try to minimize the error, but here we just need to understand, I'm gonna write it, the approximate answers differ because of the choice of the sample point. So in this case, okay, in this case, we are introducing some error. So some errors going on because we are using only a few sample point. I only choose 4. That's not enough. You actually need to choose as many as much as possible. Therefore, thus, we need to investigate how we can achieve an accurate and better answer. We need to test more. That's what they're saying. But it's going to be between some range. And then the more you are going to choose a different sample point, the gap between here, it's going to be smaller. That's the ideal situation. But here, honestly, I don't, it's hard to, choose like a multiple 10 points, 11 points. I'm just showing you the random, like a 4 basic point, like an exact corner point or exact midpoint. But I just want to give you that idea, okay? It does not give you the specific answer. We're just going to get the, approximate answer. So the more you're actually trying with more sample points, the gap will be reduced down. That's the idea. Okay, so think about it. That's how mathematicians begin to solve this type of question. Okay, I'm gonna do later using just the integral to find out the volume, but here is the information we can think and begin to think, okay? So are you guys okay with that so far? So that's, I'm gonna just maximize a little bit. That's the B and C. I'm gonna take a breath for a second. Okay, so now you might be wondering, Professor Ben, just show me taking the integral to find out the volume. Okay, we're gonna get there. We're gonna get there definitely, but we're gonna do step by step. Okay, I'm gonna give you a couple seconds. If you guys are happy, if you got that one, I love to see your invisible thumbs up. I know you guys are watching the video, so you can pause and you can rewatch, but I'm just, trying to interact with you. So are you okay so far? So think about it. Okay, very interesting introduction. So I'm gonna give you 10 more seconds. And then I'm gonna think about the double integral. Like a double integral, the integral technique is gonna be much comfortable to find out the answer in a shortcut. So let's look at that idea. Okay, I'm gonna go down slowly.
Professor, I have a
Yes,
question.
no, yes, go ahead.
I'm trying to get access to take notes, but I can really find the slides.
I post the this slide. Oh, I see that what you're saying. Sorry about that. I didn't upload it today. I'm gonna do it right
Oh,
away.
okay. Oh,
No
it's okay. I'll just give the notes later then. Thank you.
Yeah, no problem. Thank you for letting me know. I do that, but yep. Okay, so let me do that away. Do that. Yep. I just. Yep, you can find out now. You can download it.
Thank you.
All right, so let's go back. So now you might be super wondering, okay, just show me the integral. Okay, we got that. Here we go. Before we're gonna take the integral, I wanna show you a couple properties of double integral. Okay, so this is not just simple integral, this is a double integral. So let me change the color. Double integral. So let's say you're taking the integral. We have two different functions. One is f, and definitely there are two different variables. And then, we can apply a couple property, the summation first. If you want to adding and take the integral, so the double integral, you can separate it. It's the same thing. You can use a distributive property. So this is the summation. You can find out the first double integral with the f function, and then adding with the double integral of the g function. So that's a simple property. And again, the constant can be into the front. You can bring to the front. So this is the same from the integral property, like single integral property. And the next one, just be aware, the R, we have a different region. So let's say R is the, let's say I'm gonna just make a Venn diagram. So we have a set S, we have a set T, okay? And then the intersection between S and T, there's empty. So that means they are exclusive relationships. So actually this is the situation. They don't share anything. They're separate, independent, interval. If then, right, you can just find out all the summation of S. You can find out all the summation of the T, and then that is going to be the R. So that's the relationship. So if you remember the length, right? I have A to B, right? So the integral, if I have there's a middle point, let's say C, A to C plus C to B, this is the same as A to B, right? So you can think about this. I'm gonna just rewrite it. So we have three different points, A, C, B. From A to B, there is a middle point C. So A to C, this one, plus the next one, there's no, sharing thing. And then it's the same A to B. So the same thing like our S and T. Because, the reason why we are using S and T, because there's a different, interval. So simply we are just saying S and T. If there's no commonality between them, simply it's the same entire R. So this property also same thing from calculus 2. Okay, 2 more, I think 3 more. This one, we can think about it. If there is order, specific order between f and g, whatever the outcome of the f function is always larger or equal than g function, it's the same outcome with taking the integral. So same relationship, you're gonna have it, okay? Because it is already greater than or equal to, then taking the integral gonna give you the same outcome. And same thing with the sandwich theorem. This is a squeeze theorem. If m and m heading to the same answer, this is going to be the same answer. So that's a squeeze theorem. If you remember, or sandwich theorem, so that you can take a look at finding out the first and last. If they're giving you the same answer, middle will be the same. So that's a squeeze theorem as well. The last one, it's very important, okay? So in double integral, okay, you have a, let's say, you have a function f of x and y, and you can factor as a product of functions. So what I'm saying is, let's say this is a 6. This one can be 2, this one can be 3, because a 2 times a 3 is going to be 6. If you can find out the factor, or you can say x second minus 2x plus 1. We know that the factor is x minus 1, x minus 1. So here, one is x minus 1 here, x minus 1 here. You can separately multiply after taking the integral, it's going to be the same answer. So if you can be factor of the function, then it's no problem, multiply each integral, okay? So this one I'm going to show you as an example, but other than that, like 1, 2, 3, 4, 5 should be very understandable, okay? So let's take an integral, like a real double integral. So there is an order, right? So let me go down slowly. So one thing, so far we have seen how to set up a double integral and how to obtain an approximate value for it. Approximated, we cannot 100% sure, but we are estimating. We can also imagine that evaluating double integrals by using the definition can be very lengthy process if we choose a larger value for m and n, right? Because if you choose a many sample points, the process is going to be more complicated because you have to add in so many different terms. So that's what they're saying. So the basic idea is that the evaluation becomes easier if we just take the double integral, because a Riemann sum is the same as an integral. So if you take the double integral into the single integral by integrating first with respect to one, then with respect to the other. So what I'm saying is double integral, yes, it's going to be simple work rather than choosing the many sample points, the classic work. So here is the thing. Here, I have a f of x, and then I have a specific interval for the x-axis, a to b. And I have a specific the interval for the y variable, so that's the c and d. So watch me. You have a 2 different scenario. You can take the integral y variable first, then dy should be inside. And then that means you're taking the integral with respect to y first. Okay, so that's why this work gonna be happening first. Then second variable right there, dx. So this is the integral for the dx. So that's why take the y first, then later you're gonna dy. If you have a dy dx order, but you might have a different order too, right? You might have a dx first. So what happened? Dx, oopsie, dx first, right there. So a and b, then you're gonna go to the dy at the end. So there's a 2-way, depending on your question. So dy, if you want to take the first, do that inside. Then we take the take the another single integral. So we're gonna do single integral step by step twice. Okay, so that's gonna be the way we call this is integrated, just integrated integral. And let's really do some work. So let me go down. So this is not really complicated, but anyway, here, one more thing. I mean, same idea. It's the same idea how to do the integral. So, you have this work, 2 double integral. dA is dx times dy, or it's the same as dy over dx, right? Because dA is the same outcome, of the multiplication between x and y. So dx dy or dy dx doesn't matter. Actually, you're gonna get the same answer, okay? The order is just different, but doesn't matter. The outcome is gonna be the same. But here, so this one you can do dx first or dy first, doesn't matter. You will get the same answer, okay? So that's we call Fubini theorem. So actually the order doesn't matter, okay? It's gonna be the same answer, okay? So I'm gonna do that work. Are you ready for that? So for that work, actually I'm gonna do another example. So I'm gonna actually do this example first. Actually, this one is first. I wanna do this one because I wanna prove that, Fubini theorem is true. So you see that I have a function, f of xy, 3x second minus y. They say take the integral with respect to y first, then take the x later. Or you can take the x first, then later y. So we're gonna do both work. So A, we're gonna take the integral first, integrate with respect to y, then 2x. So we could do double integral fxy dA. So they want you to do first what? dy first and dx later. So if I plugging in, this one should be dy integral. So this is the dy. This is the y integral. This is x integral. So we have x is outside 0, 2, 0, 3, fx y, and actually it's a given function. I'm going to change it. 3x second minus y, and then dy and dx. Are you following? So we're going to do the inside work first. So that's going to be what happened. So this is the dx. I'm going to take the integral, so we know what to do. You're taking the integral with respect to the y variable, am I correct? So you are increasing, we are increasing one y. So this is going to be 3, x is a constant, but then this is a constant, then it's gonna be y at the end, y to the second over 2. And then this is from 0 to 3. Are we okay with that? So I'm gonna simplify that work. So what happened? You're gonna subtract outside. So this is going, you're gonna plugging in 3 into y. So this is going to be 3 second, oh my bad, 3 x second, y is a 3, minus 3 to the second over 2, minus, well, 0, everything is gonna be 0, and dx. Then 0, 2, we have 9x second. Well, this is going to be 9 over 2, 0 dx. All right, now we're gonna take one more integral with respect to x. We finished with respect to y. Now go to with respect to with respect to x. So here we're gonna do what happened? 9. You're gonna take the integral. So 9. We have x to the third over 3 minus 9 over 2x, because that's constant here from 0 to 2. So plugging in 2 into the x, because this is with respect to x. So 3 over 3, 9 over 2 times 2, minus 0. So if you calculate it, you can use decimal, doesn't matter. Actually, I did it. It should be 15. So that's letter A. You integrate with respect to y first, and then to x. So we got that answer. Does it make sense? I hope this is clear. Are you happy? So actually, I'm gonna make it larger. So that's A. I really want to check if I change the order, are we going to get the same answer? Let's see. So let me change the color. B. First, integrate integral. Take the integral or integrate with respect to what? X first, then we're going to go to Y. So I'm going to copy this. So they say, hey, take the integral f x y dx first. So x interval 0 to 2 should be inside. Then dy later 0, 3. Gotcha. Okay, so let me change the function. We have a function given 3x second minus y dx dy. So we're gonna do this work first. The inside. So what happened now? Y is the constant, so you can increase one x variable. So what happened? So this one, I have 0, 3 outside, dy. So 3x to the third over 3, right? Minus yx, because we consider y as a constant. And then from 0 to 2. So 0, 3, cancel. We do have x third minus xy. I can change the order from 0 to 2. Okay, plugging in 2 into the x. So you have 8 minus 2y. Well, 0 is a 0. So we got that answer. And then we have 8 minus 2y dy. Now take the integral with respect to y. So that's going to be 8y minus what? 2y to the second over 2. Because you are increasing 1y. So y second over 2. So they're cancel from 0 to 3. So 8y minus y to the second. We have a 0 to 3. So you're going to do 8 times a 3 minus 3 to the second and minus 0. So what happened? 24 minus 9. I have the same answer, 15. Dun, 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 dun. We have same answer. So that's why I said order doesn't matter. It's up to you which one you want to do first. So if you got that one, you just prove that the what is the theorem? We just talked about the Fubini theorem is true. Okay, so it doesn't matter which one you want to do first. Okay, but it's only applied in the continuous function. If there's a hole, there's a break. No, it's not going to work, right? Because there's a two different domain piecewise function. But anyway, we are not going to see any discontinuous function. I'm going to give you the continuous function so that you can prove this Fubini. So the Fubini theorem verified. We just prove it. I'm going to hold up here. Can you show me your thumbs up? Are you following me? Are you guys okay? Or am I talk too much? I know I talk too much, but are you okay with that? So I'm going to hold up here. I got you. Okay, don't be scared. Nothing to be scared. It should be okay. I'm trying to my best to show you all the step-by-step work. All you need to do, just make a time to review that, okay? So can I go, so we just finished all the 5.1. I show you the classic way using the Riemann sum to find out the volume. And I just show you how to take the double integral to find out the volume as well. And one theorem is a Fubini. Doesn't matter the order, you will get the same volume. I'm going to practice just 2 more. Okay, it's not going to be difficult question, but let's go up. So there are 3, but I'm going to just 2. Okay, maybe we could try this one. So they say, hey, find out the volume. The function is x. This is a very linear function, and this is so whatever the first one is x range, this is a y range. So we know Fubini, the order doesn't matter. You can do dx or dy, or you could do dy dx. Doesn't matter. It's going to be the same, correct? So let's take a look at that. We're going to take a look at that information. set it up. So I'm gonna do f of xy. We have a dA. Which one you want to do? I'm gonna just dx dy. Okay. Anyway, you're gonna get the same answer. You're gonna do dy dx later. But now we already know that you're gonna just choose one of them because they're gonna give you the same answer. So now I have the integral, and the function is just x. Thank you. And I'm gonna do dx first and then dy later. So the dx, so the x interval 0 to 2, y interval 0 to 1. So you can set it up. Doesn't matter if you do dy first, then what happened? 0, 1, and then 0, 2. Doesn't matter which one you want to do it, but I'm going to do this one. Okay. So this one you can check later yourself, but I'm not going to do it. We're going to do this one. Okay, so let me minimize it. So what happened? Take the integral with this part. Oopsie. This part. So that is going to be, so I'm gonna 0, 1, big bracket, dy. So x, thank you, because we can just simply increase, and then from 0 to 2. So that is going to be what? We have 2 to the second over 2 minus 0, and dy. So that is going to be 0, 1. What is that? 4 divided by 2 is a 2. So we have 2 and dy. Okay, now we're going to take the integral with respect to y. So this is going to be simply 2y, 0, 1. So 2 times 1 minus 2 times 0. This is a 0. The answer is a 2. Again, if you do this work, you will get the same answer. So that's how you take the double integral to find out the volume of the given function of the two variable. Sounds good? So the actual work, it's not that complicated, but I want you to understand what we talk about at the beginning, why, and think about the image. It's not really abstract concept though. I'm gonna do just one more example. Are you ready for that? So let's take a look at one more example. I think you could do it yourself, but I'm gonna help you. Anyway, by the way, are you okay? I'm gonna hold up here for a second. If you're happy, I'd love to see your thumbs up. Does it make sense to you? Yay, good celebration. So one last question for today. Here we go. Okay, we have a function. Thank you. They already set it up. So it doesn't matter which one you want to do. You can do dx, dy, but I prefer to do dx, dy because x is always a simple number. So anyway, we have this. We have xy minus 3yx, and then I'm going to do dx first. So if you do dx, write down the interval 0 to 2. And then dy later, 1 and 2. So what happened? I'm going to do inside first. So this one, 1 and 2, big bracket, and we have a dy later. So take the integral. So many people a little bit confused. Consider whatever the other variable as a constant, right? So you can think about the same thing, partial derivative. This is a partial integral because we are dealing with two variables. So you're going to consider y as a constant, okay? But I can actually make it a little bit easier if you want, but doesn't matter. Let's keep on going. X, y, so y is a constant. So y is still there. I'm going to increasing x to 2. And then 3, y second is a constant, doesn't matter. We're going to keep it and divide it by x to the 2 over 2. And then I'm going to just bring this one here. We have from 0 to 2. Are we okay with that? So let's plugging in. Once you simplify, so 1 and 2 here. We have a dy later. I can do, this is x second y over 2, right? Minus what? 3 over 2, x second, y second. Now you're going to plugging in 0, 2. Okay, keep on going. We're going to plugging in 2 into the x because we took the integral with respect to x. So 2 to the second y over 2. 3 over 2, 2 to the second, y to the second. And then we know the 0 is going to be 0. So I'm going to make a space so that it's going to be 1, 2, cancel, cancel, 4 divided by 2, 2y. And then this is going to be 4 and divided by 2. It's a 2 times 3, 6y to the second dy. Now we're going to take the integral with respect to y. So 2y to the second over 2 minus 6y to the third over 3 from 1, 2. So simplify, thank you, thank you. Y to the second, 2y to the third from 1 and 2. So you're going to plugging in 2 to the second minus 2 times 2 to the third minus 1 to the second, 2 times 1 to the third. So this is capital F of 2, capital letter F of 1. So anyway, 4 minus, what happened? This is 8 times 2, negative 16. Minus 1 minus 1 to the third is 1 and 2. So we have negative 12 minus, we have a negative 1. Dun, 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 double negative, change it to positive, beautiful. So we have a negative 11. So this is the answer. Okay. So you can finish up this. Again, if you change it dy or dx, the answer is going to be the same, negative 11. So that's it. That's how you're taking the double integral. Nothing is special. Definitely you can handle it. I have just, one more example. I'm going to go down here. By the way, I'm going to hold up. Anybody has a question? Are you happy? Are you happy? Yes, yes, yes. Okay, sounds good. As long as you're happy, I'm happy too. All right, let's take a real last question. Sorry, just real last question. So this one, a little bit tricky, okay? Because you feel like, oh my goodness, there's a 2 function e to the y and cosine x per specimen. Should I have to use a product rule? No. So there's no product rule in double integral because of this fact. Let me go up, 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 up. Do you remember this one? I actually highlighted. Whatever the given function, if it can be factored, right? 6 is the same as 2 times 3. So you can factor 2 and 3. That's your factor of 6, or x to the second minus 2x plus 1. The factor is x minus 1 times x minus 1. If you can find out the factor, just simply separate them based on the 2 different factors or 3 different factors. So because of this fact, what do you guys think? You don't need to take the product rule. This is a great example. This is the great example, the property. I just show you property, the last one, okay? Because this function is clearly by the 2 factors you can find out. So what I'm saying is, this is the function e to the y times cosine x. This is the factor. This is like a 2 times 3. So you have a factor. One is e to the y. Another one is a cosine x. Nothing is special. These are just factor of this chunk. We already see the factor. This function is clearly, I forgot the factored by the by 2 factors, right? So we have 2 factors right there. So what happened? Simple. You can use the property I. So the double integral e to the y cosine x equal to, one is e to the y, right? But it's up to you. I'm going to just write it everything. You can do whatever you want. You can start dy, dx. Doesn't matter, as I mentioned. I'm going to just dx, dy order. So what happened? You can separate it. E to the y, right? Because you can combining this one with the dx or dy. Doesn't matter, but I'm going to make the same variable, just dy. And then times integral, what is a cosine x? You can be with the dx. Okay, does it make sense? The order doesn't matter. You're going to get the same answer. I'm just make it a little bit easier because y, I just want to take the integral with respect to y because of the x. I'm taking the integral with respect to x. Doesn't matter. You can change x and y. You're going to get the same answer, just more work. But I'm just make it simple. Y can be with dy, x can be can be with dx. So that's what the property said. You can separate it because we have a two-factor. You can separate it and multiplication. So we know the y interval is here, 0 to 1. X interval, 0 to pi over 2. So simply, e exponent is always the same, whether you're taking the differentiation or integral. So e to the y from 0 to 1 times cosine. When you take the integral, do you remember? Positive sine x from 0 to pi over 2. So that's it. You're going to calculate that. This is e to the 1 minus e to the 0 times sine pi over 2 minus the sine 0, correct? So actually, I'm going to bring this one here. Leave it at, that's okay. So e to the 1 is e to the 0 is minus 1. And then you multiply what? This one. Can you go to the decimal or just check it out? This is a sine function. Here, pi over 2, this one gives you 1. So this one times 1 minus sine 0 is a 0. So therefore, e minus 1 times this is 1. The answer is e minus 1. That's all. So be careful. The last question, if you can be factored, if the function can be factored by 3 or 2, just if you have a 3 factor, just multiply, keep multiplying. So this is a unique property that exists only with the double integral. Okay, so that's all I want to say. I think we finished 5.1, so I'm going to hold up here. I think we are doing a great job. So 5.1, chapter 5 is all about double integral, and I'm going to keep changing the function. So, next week, definitely we're going to talk about the 5.2, double integral. Chapter 5 is all about double integral, triple integral. So we're gonna look at more benefit of using the integral in many different contexts. Okay, so I just introduced the double integral. As long as you can figure it out how to take the double integral, that's good. That's good enough in 5.1. Okay. Just I talk a lot, from the background, where it came from, the formula, where it came from, Riemann sum, and I show you a couple theorem, but calculation should be easier, right? So I think that's it. That's all I prepare for you.